Hello everyone. I hope the audio is right this time, okay? I hope the stream quality is good. Hello everyone. Okay. So see, uh, every doctor, every optometrist, every optician, every every eye specialist says that myopia cannot be reversed. This has been scientifically proven. So they say that it is scientifically proven, but I want you to understand that there is no such thing as proof in science. You can only show that something is verified or valid, scientifically valid. Okay. But there is no such thing as proof in science. There are only local evidence which are valid only in the conditions given. Okay. You have not, to prove something, you have to account for all the possible conditions, possible variables, everything. Then you can prove anything, otherwise not. So before I begin, I want to tell you that these everybody say that myopia cannot be reversed or what, but there is still no well-established cause of myopia. If you Google cause of myopia, you will only be pointed out to result that say what happens in myopia, not what causes myopia. Okay. So for example, this result, it clearly says while the exact cause of myopia is still unknown, there is still no well-known cause of myopia. So there are multiple factors to keep in mind, multiple things to keep in mind. So I will develop a theory later. The theory is still in the research paper. But at this point, it is sufficient for you to understand that there is no well-established cause of myopia. There are evidences, but the cause of myopia is still unknown, okay? But still you are claiming that myopia is not, but still you claim that myopia has been proven to be not reversible. That's not true. You have not proven, you have only shown that under this and this such and such circumstances, myopia has not been observed to reverse, okay? You have not taken account all the cases. So to to even begin to understand myopia, you need to understand how lenses work. Like this is a lens. How does it work? You need to figure out. Your eye is a biological organ that sees things, okay? That is responsible for seeing things, vision. Before you even begin to understand that, you need to understand the physics of optics, specifically geometrical optics, okay? So this will be the goal of this video, to detail some of the assumption, how we describe lenses and this, and what we mean by an object and its image. So these concept needs to be clear before you want to understand what is myopia. You need to your concept need to be clear on what is an image, what is an object, how images are formed. Okay. So this is a simple concave lens. Okay. Uh, just like a mirror can either be concave or convex. Okay. If you So what is a plane mirror? A plane mirror, see, a plane mirror can be said to be either a concave lens or a convex lens with very large radius. Okay. A plane mirror becomes a special case. Similarly, a lens can either be concave or convex. Then what is a flat sheet of glass? A flat sheet of glass just a lens with a very large radius or very low power. Okay. Fundamentally, there are only two types. The flat sheet of the flat, what we call the flat case or the flat sheet of glass is just a limit, stretched, just a limit of a concave or convex, whatever lens you prefer. Okay. So, so this is a simple lens. It has only two fundamental, I mean, parameter or characteristics. One, its principal axis. Okay, so this is a planar lens. The lens you can see is shaped like a plane. Okay, so this is a planar lens and there is a principal axis going through its optical center. So the principal axis lies vertical to this lens. You need to understand. Okay, and the lens has an aperture. Okay, lens and aperture are the only two fundamental properties of a lens. So if this lens is a diverging lens, then its focus will lie somewhere on its principal axis. If it's a diverging lens, then light rays will diverge or seem to originate outward from the focus. If it's a converging lens, often called as convex lens, then light rays will appear to converge at its focus. So before we talk about how this lens forms an image of this object, this is a pen drive. Okay, before we talk about, you need to understand what is meant by an object and image point. So each and every point on this object emits light rays in all directions. Okay, and only a fraction of them, not all of them, only a fraction of them hit the lens. So you can see in this picture that this is the case. Okay, and as the distance between them gets bigger, the amount of light being received by the lens aperture becomes smaller. If you can increase the light by making either the object closer or making the aperture bigger. Okay, both have the same effect, or you can say both will have the same effect. So similarly, an image point can be defined. So if this object and this lens together form an image, then every point on that image will act as an image point, can be said to be an image point. Okay, so an object point emits light rays in all direction. An image point can be said to receive the rays emitted by an object point, not an object point onto it. Okay, you can also say that an image point rays emitted by an object point terminate or converge. Okay, so these are the basics of the geometrical optics. You need to understand this. Okay, an object can exist without an image. Okay, an object can exist, but for an image to exist, an object must also exist. An image cannot be made without an object. Okay, so if you want to understand, so if you say you know the focal length of this lens, okay, so what is a focal length? So you can make a very basic assumption that a lens like this converges all light rays parallel to its principal axis to a single point. Okay, and this focal point lies on its principal axis, and the principal axis in itself is perpendicular to the profile of the lens. You can see this is a planar profile lens, and the principal axis will be perpendicular at 90 degrees to its profile. And aperture determine how much is the admission area. So if I cut this lens smaller around this optical center, it will not affect the lens, it will only decrease its aperture. Okay, the lens does not change, the focal length does not change, its principal axis does not change, nothing changes, only aperture changes. Aperture can be made bigger, smaller, you can make it. And it mostly does not matter when it comes to geometrical optics. When we are concerned with image distances, aperture mostly does not matter. It only matters when you want to calculate depth of field. We will talk about that in some later live video. In this sense, an ideal lens is a theoretical object. It has only one task to do: to converge all light rays parallel to it onto its focus or diverge it away from focus. Okay. So in my research paper, you will see only one case mentioned: a convex lens, a converging lens that converges all light rays to its focus, not from its focus. Okay. So if you want to derive the relationship between, say, this is an object, then what will be and this is an object, and the distance from lens optical center is this one, then what will be the distance of its image? If you want to derive that, you need to take two assumptions. The first assumption I have already mentioned: all light rays parallel to the principal axis of lens converge to a focus, converge to a one point that will be called its focus. And the second assumption is that a light ray that passes parallel to, see, if a light ray passes parallel, if I orient this lens vertical like this, a light ray passing parallel to its profile of the lens will not happen, will remain unchanged. Nothing will happen to that. It will pass unchanged. This also implies a hidden assumption that a light ray at some angle to the lens will have both parallel component and a normal component. The normal component passes through the focus and the parallel component passes unchanged. Okay. So in these images, let me show you better. See, the assumption A: every light ray parallel to a lens passes through the focus. Okay, and if a light ray makes some angle, it is not parallel, then its parallel component will pass through the focus, and its normal component passes through the focus and its parallel component passes unchanged. These two assumptions are sufficient, are everything that you need to know that how a lens makes image. So you can see that if a light ray makes angle like this, you can calculate its parallel and normal component, and then apply that to get how this lens forms an image. Okay, so if you open your textbook, like school textbook, you will see that a light ray passing through the optical center passes unchanged. We do not need that. See, this case number 2, a light ray is passing through the optical center of the lens, but this can be explained by the combination of our assumption. This light ray will make some angle. It has a parallel and normal component, and it will result in the same angle on the other image ray. We do not, so in a way, this derivation is more fundamental and more elementary than your high school textbook. Okay, so you can see that these two assumptions explain each and every light ray incidence, every case of light ray incidence on a lens. You can see in this picture. You will also find it in figure 8.5. So you can see that you can apply these two rules to calculate how they will meet after an image point. Okay, using only these two assumptions. Assumption 1, every light ray parallel passes through its focus. Assumption 2, a light ray can be broken down into its parallel and normal component. The normal component passes through the focus, parallel component passes unchanged. Okay. And and you can then derive the lens formula based on this. So if you go and watch a derivation of lens formula, so if you search Google for derivation of this lens formula, how to calculate the image distance when the object distance and the focal length of a lens is given. So it will go like this. You make some triangle and this and that. We do not need that here. Because this is a better and more fundamental derivation, I will show you a better and more fundamental relation that does not involve anything. Okay. You only need to consider two cases. Okay. When an object lies closer to the focus, or when an object lies beyond the focus of the lens. You need to consider only two cases. If you consult a high school textbook like NCERT, you will see that they consider cases like 2A, yeah, or 2F. 2F means the spherical radius of curvature. Ideal lenses are not spherical. Please understand. There is no such thing as sphere. If you are watching this video, you will not see that. You will see that I do not need to explain the lens as a sphere to explain how a lens converges an object. To see, okay, you do not need to understand. You only need to assume that a lens is a magical device that converges each and every parallel light ray onto its focus. You do not need to assume it's a spherical, and real lenses are never spherical. They will be a spheric lens. Okay. Real lenses are always aspherical. So you can, if you are interested, you can read this. Go and read this. Okay. This is a spherical lens. Real lenses are never spherical. You only need to assume that a lens has only two properties. One, I have already said enough. So how do you want to, so using only these two properties, you can then consider these two cases where an object is located closer to the focus or beyond the focus. Okay. And then you will get two image formation possibilities for a convex lens. Okay. Converging or convex lens. You will get two image formation possibilities. If an object is at focus, nothing will happen. These two light rays will never meet, and you can simply ignore them. This is not possible. An object will always either situated closer than focus or beyond that focus. Okay, so we'll consider cases 1 and 3. So in case 1, when an object is beyond the focus, you will see that the light ray that is parallel, light ray that is normal, exactly perpendicular to the lens aperture, passes to its focus. We have already said that in assumption. And you will also notice that the light ray that passes through the optical center of the lens passes unchanged. We have already derived it as consequence of our two assumptions. Okay. And then you will see that the angle between these two rays, the red ray and the brown ray, is less than, you can say, is less than 9. How you can see that the angle between them is less than 180 degree. Okay. Similarly, if an object is farther than the focus, sorry, closer than the focus, you will see that the ray that passes through the lens parallel, normal to the lens profile, and the ray that passes through an optical center, they both make an angle greater than 180 degree. Okay. On the opposite, they both meet on the left side of the lens, or opposite to the direction of light, you can say that. So if you remember something, you will see that you can say that in the first case the lens makes real image. In the second case the lens makes an virtual image. But I have already said that an object emits an object is where light rays are emitted, and an image is a point where light rays converge. Is this virtual image light rays are appearing to converge or diverge? If you think carefully, the light rays from this virtual image, what we in this so-called virtual image, light rays are appearing to diverge. So I think it is better and more consistent to call this as virtual object, not virtual image. Okay, wait. So do not assume that you will learn everything by this video, by watching this video alone. You have to read what this research paper says, how this formula is derived. Okay, so we need to be concerned only about real images, and real images are only formed when the angle of convergence is on the opposite side of the lens away from the object. A real image is formed only when. So your high school calls this as virtual image. I think it is better to call this as virtual object. So there is only one thing, an image. So there is only one thing that can be called an image, and you call it real image. I will call it just as an image. An object can be either virtual or a real object. But an image there can only be one image, only real image. What you call real image, there can only be one image. Okay. So then you can just derive using these two assumptions. And if you derive, you will see that the formula will come. I will not cover the derivation in this video. You can just go and read this image. Pen, copy, paper, write it and understand how this formula is derived. Okay. So this is the better theoretical understanding that you need to understand geometrical optics. Even your high school textbook misses some key points that are needed to properly understand geometrical optics. Okay, and this will only, I mean, handicap. This will be your handicap when we will understand, when we will move on to better, I mean, higher, like when we will move on to higher concepts, like the like what happens when we increase power of the lens, what happens when we shift the distance between image and the lens. So you need to have this foundation before attempting the section 2 in the research paper. You cannot just go and read, you will not understand it completely, in my opinion. Okay. So if you already know the lens formula, assuming you understand it well and you have derived it, you know how it works, you can assume, like, see, this is an object. If it, you can assume object distance to be multiple of focal length. You can express. So if an object is located at a distance twice of the focal length, you can say that object is located at distance 2. This is called dimensionless object distance. Okay. And you will find this concept helpful when it comes to explaining why image and object uh, have this certain relationship. So if you use this, if you derive this formula, if you consider an object distance as the dimensionless object distance, you will realize that the image and object distance follow a hyperbolic relation. Okay, simple hyperbolic relation. This is a very theoretical relation. Simple hyperbolic relation. So, and I mean, and the closest they approach is at point 2 comma 2. And from there you can see some results. I will not, I will implore you, I will encourage you to read the research. So put simply, this formula is the reason. This formula is the reason. Can you see the denominator? J is equal to k upon k minus 1. The denominator cannot be negative, means k must be greater than 1. What is implied? For the formation of a real image, the object must be located farther than its focus. Simple. Okay. The dimensionless image relationship makes it clear to understand why some things are why some things in physics behave the way they are. And this dimensionless image relationship explains why you cannot say, if you want to make an image of an object which is located from a lens at a distance x, and similarly you want to receive its image at a distance y. It shows that this distance, the sum of the distance cannot be lesser than the, I mean, 4 times of the focal length of the system, of the lens. This distance cannot be less than 4 times of the system. You will see this is what this graph signifies. Okay. If you want an object and you want to receive at a distance at its image, say you want to design a mobile phone camera, you want to image an object at this point, okay, and this the lens and the image are need to form in this within this 1 centimeter. You need to use that formula to determine what will be the focal length. This formula will be always obeyed. This is a simple, sorry, not a simple, this is a fundamental limit on how physics works. And you will not find this formula without with the main law. You need to consider the dimensionless relationship for this formula. So I think this video is a little too much. Okay, we will talk about if you understand this, if you have seen so far and you understand this, the simple lens formula and the dimensionless relationship between image and object distance, I think you have you will gain some understanding what the section 2.3 says. Okay, 2.2, and you will understand what will section 2.2 and 2.3 want to say. How, I mean, how systems become myopic and hyperopic. You will gain a better understanding. This is what physics does to you. Okay. So I think we will discuss section 2.2 and 2.3 in later video. You can, this video will be just an introduction to geometrical optics. Okay. Bye. Bye.